things that we have worked in the recent past in my lab. I don't know how far we're going to get because we have 25 minutes, but we'll see. So these are the current students, including Matthew, that is back there, who is soon to be graduate student. And I'm not going to talk about what Matt is doing because we're not going to have time. But I will give you a sample of some of the other stuff that we're doing. The first topic is we call Flow GSP and Flow GSPAN. So GSP, as many of you know, is a well-known data mining algorithm. And so what we have been doing here is mining flow graphs. Why are we interested in mining flow graphs if we are compiler laboratory? The idea here is this work is done with a bunch of people at the IBM Toronto Software Laboratory. So a couple of years, several years ago, 3 or 4 years ago, Adam did this work that consists in the following. The whole idea is that we often have a compiler developer that is sitting at a desk, staring at a computer screen, and doing all kinds of experiments to try to find opportunities to do better transformation in your code, to generate better code from your source code. We believe that there is a better way to do that. That is to ask a machine to do it. And so the whole question is how we find these opportunities. So here is one concrete example of a place where you may want to look for opportunities like that. IBM has this very large piece of enterprise software called WebSphere. And WebSphere provides basically software services to companies. This WebSphere software runs in fairly large machines that are the old style big iron machines that some of you might never have heard of, because we think that everything runs in clusters these days. But when WebSphere runs these big machines, it has to be compiled with a compiler. And that compiler in this case is actually WebSphere is written in Java, is the test browser Java compiler from IBM. The run of that application in this machine produce a large amount of data. And what we had prior to our work was the engineers dumping this data into basically spreadsheets that are not much different than Excel spreadsheets, and then generating very sophisticated queries to this spreadsheet asking, is there a correlation between a branch misprediction and a pipeline interlock? And questions like that. So it always depended, or was always premised on an engineer thinking of a possible correlation that could exist, and then writing a query to this very primitive database. Of course, the managers are asking, have we gotten everything? Are there things out there that could be an opportunity that we are not seeing? And the motivation for that is, in the olden days, we always told compiler students, do not worry about code that's not inside loops. That the only code that really matters are the code that's inside loops. So we could classify our code into hot portions of code that are represented with warmer colors, and cold portions of the code that are represented with blue colors. And if something is cold, don't worry about that. Because the real game is in the hot code. What we see today in this enterprise software is that we have very large code base, and if you try to profile one of those very large code base or a large piece of enterprise software such as WebSphere, you're going to find out that there is pretty much no hot code. There's nothing that's hot. Then you may think, well, then there is no point on trying to focus on something because I don't have something that is repeated a lot. Actually, we still have things that are repeated a lot because these large code bases are built by humans. And humans have this tendency of building templates and then applying those templates over and over again when they are solving problems. So the templates are there and they are being repeated, but they are not in one place of code. They're actually spread all over the code base. And so what we use data mining to identify these pieces of, these templates of code that actually are executed a lot, but you cannot find a guilt part of the source code that can attribute to. So Adam's work was to adapt to GSP, that is a very well-known data mining algorithm, to work in these flow graphs. The flow graphs are used to represent your project. What Carolina is doing right now, and she's not here today because she's actually in Toronto presenting her work at the industry exhibit at the CASCOM. What she did was adapt another data mining algorithm called GSPAN. That's why we call the new piece of work called GSPAN. And the idea now is that so far we have applied these data mining techniques to mine and provide advice to the compiler developers. What we want to do now is to move this data mining technology to provide the help to the programmer. So that would be mining at a different level. We will no longer be mining the hardware counters that we produce, but we will be mining instrumentation counters that are inserted by the programming helping tool. So that was about FlowGSPAN and FlowGSP. Another piece of work that we did recently, it was done by Ricardo Sanchez, is to use machine to learn method-specific compilation strategy. Again, in Testarossa, that is the IBM Java compiler. So the whole idea, first I have to tell you very, very briefly about Testarossa. Testarossa is a Java compiler, and when you're compiling Java, you have a repository of class files. Then you're going to have an intermediate language generator that will convert those class files. And then you're going to have an optimizer that will transform that representation. And then we're going to have a code generator that will generate the code. And then you have the compiler methods. This is the simplest, highest level that I can put the work that one of those compilers does. In the case of Testarossa, it is not your grandfather's compiler. It has a compilation control mechanism, and it has to generate code for a whole bunch of machines, from the IBM SP90 to PowerPC, ARM, x86 bits, and many others. So this is a very mature compilation infrastructure that is used in industry. So the way to put the problem here is that first we're going to do some data collection. So we're going to have interpreted methods, and we're going to generate something that we call modifier queue, and I'm going to tell you in a minute what those modifiers do. Then these interpreted methods will be run by the virtual machine, and at some point the virtual machine will decide this method is important enough that I'm going to send to my just-in-time compiler for compilation. At that point, the compiler has to come up with a compilation plan. That is, each one of those bits is telling the compiler which one of the code transformations that the compiler has available itself should be used for that given method. And then we're going to add to this picture here a strategy control. And what the strategy control is going to do is we're going to go into this modifier queue, and we're going to get one of those modifiers on the queue. And now it will do an AND on the modifier with the compilation plan. So what the strategy control is telling the compiler is actually don't do everything that you talked about doing. Turn off some of the things. And this is a way to build mechanisms for us to explore the space of possible optimizations that we could do when we do compilation. And then we have our compile methods. So by using this mechanism, we can generate a significant amount of data about what each one of these code transformations that the compiler can do does to the performance of the method. We're going to also collect features about the methods to say, oh, this method does lots of floating point computation, this method has lots of tested loops, this method does lots of dynamic dispatch, etc., etc. So now we're going to be able to associate the features of the methods with how well they do with these modified compilation plans. Also, we have done that. We use support vector machines. If you're doing machine learning 500 level course, probably you heard about that. So we use that method to build a learned model. A model that now I can give the features of the map that I want to compile, and the method is going to tell me which of the transformations should I turn on. So the learn method will come up with a plan, and we're going to tell the compiler, based on what we have learned from our exploration and using SPM to train the classifiers, this method should be compiled with this, and this transformation on, and all the other transformations should be off. Okay? So this work was implemented again in the Testarossa compiler, that's the commercial compiler for IBM. It was published and very well received at Code Generation Optimization, which is a top conference in this area. The next thing that I want to tell you about is the work that Prof is doing, and one of our undergrads also working on it, Adam. And the idea here is more or less the following. We often have a system that we want to evaluate. In this system, usually to evaluate what we're going to do, we're going to get a collection of applications that we deem to be representative of the usage of that system. And then we're going to obtain some metrics about the system based on running these applications in that system. So this is done throughout our discipline. Whether we are talking about a network processor, whether we are talking about a compilation system, an operating system, etc. Throughout our discipline, we use a methodology like this. Of course, some people use different methodologies based on queuing theory models or other kind of models, but often in experimental computing science, we use a methodology like that, where we're exploring a space of applications. What we often don't say or don't think about is that these applications have data inputs that influence significantly what they do. So for example, if I'm doing a file compression and I give that file compressor a text to compress, this will be a much different problem than compressing an image file, for example, or a sound file or something. So what this work focuses on is what the influence of the inputs on the behavior of those applications. But often in our discipline compilers, we actually don't deal with applications, we deal with benchmarks. The question is the same. Do the inputs influence the behavior of the benchmarks, and therefore it could influence the metrics that we get? So we are actually concerned about benchmark inputs. So early on, we asked these questions. Do the inputs to programs or benchmarks really matter? And the answer was, if we take a look at one instance of feedback directed optimization, that's what we did several years ago. This is pretty much one graph that summarizes Holberg's master's thesis. And what we did is study several benchmarks using the Ateneo architecture. And this is a graph for BC. And what this graph is showing you is how much faster the dynamic optimization is compared to the static optimization. If I use, for example, this one input, combine an input for training, and then I test over all the other inputs, and I get something like 8.5% faster. As I change the input, the gain that I can report in my paper changes. Okay, so if I got an static input, I will say, oh, this dynamic transformation that I did doesn't buy me anything. So the answer here is clearly thus, and this was a paper at ISPAS in 2006. So now that we know that the input does influence what the transformation do, let's see what we have. We have a bunch of application inputs, we have the application code, we have the compiler, and we want something like this. What do we have to do to generate this? We have to do this. We have to take the application code and the application inputs, and we have to run the code to the compiler and tell the compiler to instrument the code so that I can get the information that I want. and that gives me this instrumented code version. Then I'll take one of my inputs, and I'm going to run through my instrumented code, and I'm going to obtain some kind of profile. That's the profile because of that input. And now I'm going to call this input my training set, and I'll call these other inputs my evaluation set. Okay? So now if I want to evaluate, what I have to do is to get to this input, this profile here that I got to that input, add application code, give to the compiler again, and now tell the compiler, now I want you to do feedback directed optimization. I want you to use the information from that previous run to improve this code. So this gives me hopefully a faster optimized code. And now I'm going to take each one of the inputs and I'm going to run to my optimized code. And this will give me the performance for that input, given that I have done the training with this input. Okay? So that's the process that I have to do. Also, I have done it all. I got the value for this bug. I need to repeat the whole process for each one of the other bugs. Okay? So that's the way I need to do if I do correct evaluation of feedback directed optimization. So that was a paper in 2007. That paper actually got the best paper award in that workshop. Now, what happens if you have lots of inputs? You cannot afford to do that process for thousands or hundreds of thousands of inputs. So if you have lots of inputs, you have a situation like this. Then what you want to do, you want to cluster the inputs based on their characteristics. And their characteristics is determined by what decisions does the compiler do based on that input. So you do the clustering, and then when you need to evaluate your compiler, we'll randomly sample and take one input from each one of the clusters to evaluate how well your compiler is doing. This work was published in CDOL in 2009. So the next question now is that what I really want is not to use one input for training and testing all the other ones. What I want is to use n minus one input for training and testing the last one. Because I want all those inputs to influence what my compiler is doing. So to do that, Paul developed what we call combining profile. And there is a whole paper that you can read, but the bottom line is that we decided to use an empirical distribution to aggregate the data. And it can be boiled down to a very simple figure. When you do one run with one of those inputs, you can put the measurements, for example, for one of the counters in your profile into a histogram. And then when you do the run with a different input, you get a different histogram. And now you have the task of combining those two histograms to see what the influence of the two inputs is. And to do that, you're going